In the in the first lecture on AC, we have discussed the basic things related to the AC circuits, and we investigated how the pure circuit elements respond to the applied external AC voltage. The summary of the earlier class is that when a reference voltage V0, reference voltage is Vt is equal to V0 e to the power j omega t is applied, then we find that for resistance it is IR is equal to I0R e to the power j omega t. For inductor it is IL is equal to I0L e to the power j omega t minus pi by 2. For C it is I0C is IC is equal to I0C e to the power j omega t plus pi by 2, where I0R is equal to V0 by R, I0L is equal to V0 by XL, and I0C is equal to V0 by XC. Now R, we know the resistance, and XL, the reactance is omega L. XC, capacitive reactance, is 1 by omega C. Note that for omega is equal to 0, XC is infinite, that is, a capacitor is said to be a DC blocker. For DC signal, T is infinite, so omega is 0, and since omega is 0, XC is infinite, so a capacitor offers infinite resistance to the passage of a DC current signal. Now I come to the phase factor. Phase factor is 0 over here. The phase is lagging behind, so this is pi by 2 and this is plus pi by 2. The Phasor diagram is that if we have the reference voltage, this is the voltage, this is IR, this is IL, and this is IC. The Phasor diagram these are the Phasor diagrams, and this is lossy element. This is not a lossy element. This is not a lossy element. In inductor and capacitor, the circuit element receives energy from the source in 2 quarters and returns it back to the source in the other 2 quarters. So this much we have done in the earlier class, and we said that the reference to the investigation of the currents in an AC circuit with reference to a voltage is applicable when the circuit elements are connected in parallel. That is, say we have a resistor, an inductor, and a capacitor are connected in parallel. So the same voltage is applicable to the ends of all the 3 circuit elements. So we consider that it is as the reference voltage, and how the current through these circuits respond to the reference voltage. We have made the analysis. Now we come to the calculation of reference current, that is the response of the circuit elements, different circuit elements with reference to a current. This theory is applicable to the series combination of the circuit elements when the circuit elements are connected in series, same current flows. So we generally speak of reference current. Now for R, here since I is being supplied, our objective is to find out the corresponding voltage. So VR, simple relation, VR is equal to R times I. This is equal to V0R e to the power j omega t, where V0R is equal to R times I0. And we see that I and VR are in phase. So I and VR are in phase, that is phi is equal to 0. The phasor diagram would be, if this is by the current phasor, the corresponding voltage phasor across the resistor is this, and the graphs this is the I curve, reference I curve, this is V curve, and the power curve is positive all along. This is P curve. So power is being dissipated. Now come to the case of inductor. If we consider the inductor, then we know the basic relation is VL is equal to L DIL dt. So I is the reference, so VL is given by L di dt. Since I is the reference one, we have omitted the subscript L on it, and so we get j omega I0 L j omega t, which we can write as you know that the corresponding definition is V0R is equal to I0R. And this can be written as V0L e to the power j omega t plus pi by 2. Since this is real quantity, we see that VL leads over I, VL leads over I by pi by 2. So if we if we draw the phasor diagram, this is the I phasor and the corresponding VL phasor would be this, and the magnitude of this is given by this much, and the graphical representation would be four quarters. This is the time axis. This is I, reference I. This is V, the curve is sinusoidal. This is V, the power is positive in this half, negative in this half, positive in this half, and negative in this half. This is power. And lastly, the capacitor. The capacitor is this. We have a capacitor C and a reference current is there. What is the voltage across the capacitor? We know for the capacitor the basic equation is R IC is equal to C dVc dt, or Vc is equal to 1 upon C integration IC dt. For reference current, I omit this and we write Vc as 1 upon C I dt. So this is I0 C to the power j omega t dt, and this is I0 upon omega c e to the power j omega t. We call it minus j P0c e to the power j omega t, where P0c is equal to I0 times xc is equal to I0 omega c, and we can also write it as V0c e to the power j omega t minus pi by 2. So we see that Vc lags behind I by pi by 2. The phasor diagram would be, if this is by the current phasor, the corresponding Vc phasor is this. The graphical representations of the current, voltage and power are denoted by this. This is current, and you see that this one, the Vc lags behind, so Vc will appear its peak over here. So and the power curve would be this is the power curve. Again, over a complete cycle there is no power dissipation and the power factor is 0 as pi is pi by 2. So let me summarize again the facts related to the response of pure circuit elements to a sinusoidal current. This is reference current. The circuit elements are R, L, C. The VR is equal to V0 R to the power j omega t. This is the interesting. I am not going to the definitions of V0L and this. Rather, this is the current phasor. This is VR phasor. this is VL phasor, and this is VC phasor. And a comparative study with the reference voltage would be very helpful. The phasor diagram would be note the difference between these two and these two. These are very important. When we want to study the series circuit comprising of LR series circuit, say we have an LR series circuit. Fed by an, so since they are in series, so same current flows through it. So same current flows through it, so we are going to apply this theory. So at a particular instant, if this is the direction of the voltage, this is also the direction of IR, and this is also in terms of currents, this is also the same voltage is applied. So this is the these are connected in series, so the same current flows through it. So we apply this theory. This is the voltage phasor, so this is the VR phasor, and this is the VL phasor. So the phasor diagram is this. When we add these two vectorically, we must get this. So in the vector notation, VR plus VL must be equal to applied voltage. And if we connect these the same two elements in parallel, and it is connected with an AC current source, so same voltage is applied across its end. So at a particular instant, this is be the current phasor, then the current across this is the inductor L and the capacitor. This is IR, and this is IL. So here the complete notation will be this is the applied voltage V. And here the phasor diagram will be this is the phasor diagram. So this method we shall from the next class onwards we shall apply this method to to perform analysis of circuit of different types of circuits fed by AC sources, either current source or voltage source, as the case may be.